Good morning, everybody. Welcome to the webinar we're doing today. We have Brian Soliday with us, who's the Chief Revenue Officer of Voxelmaps. So I'll hand over to Brian to do the introductions.
Thanks. Appreciate that, Peter. So what we'd like to do is we'd like to initially welcome you to the Voxelmaps webinar series. So this is the very first webinar in a series of 4 that we're putting on. And the series is called Enhanced Decision Making via Voxel-Based 4D Volumetric Digital Twins. All right. So what we'd like to do is to go over a number of activities and case studies and projects that we've done. We're also going to get into a little bit about the overarching structure of the organization. So Peter's going to give us an overview of Voxelmaps, talk a little bit about maps for machines, which are really, for a lot of the people that are attending, is really a new concept, right? And so Peter will talk about the way that we collect the data and process the data is really geared towards machine learning and using that technology. A little bit of volumetric mapping 101. So again, it's somewhat unique to a lot of people. A lot of people don't know what voxels are and how they can be used, and we're going to kind of dig into that. Talk about our data collection tools and systems and the process that we do that. An exciting topic today will be a briefing on this 100 cities DAS data set that we're embarking on in terms of a very extensive data collection across the U.S. I'll come back on and we'll review some industry use cases, and then we have questions. So if you do have questions, down at the bottom of your display is a Q&A button, and that's where you can just go ahead and just type in any questions that you have. We'll address those at the end of the event. We're recording the session as well, and we'll be providing this to everyone after the event. So I just ask, please feel free to pass this along to your colleagues that couldn't make that today. Okay. So with that, I would like to introduce the CEO of Voxelmaps, Mr. Peter Attala.
Thank you, Brian. Thanks, everybody. It's great to be here today and have the opportunity to tell you a little bit about what we're doing at Voxelmaps. So I'm going to get started just by giving a little bit of background on the company. So the company is actually a spin out from a previous mapping company that I founded back around 2007. That company was called NavMe, and NavMe was a very early navigation and mapping company. We mapped 180 countries around the world, which is almost the whole world. It was a huge project involving about 7 billion kilometers of data and tens of thousands of people over a 10-year period to build. But about 5 years ago, we had a division of that business that was really thinking about the future of mapping. And that really became Voxelmaps. So we spun out of NavMe. We set up, we're headquartered in San Francisco, but we've grown quite well since we did that. So San Francisco is the headquarters, but we have offices in Latin America, in Mexico City, in the UK, in Nottingham, in Porto, in Portugal, and Singapore and Australia as well. So we're about at 350 people in quite a big growth phase in terms of what we do and how we deliver. Still, the majority of the work, the majority of the focus is very much on the US and North America. And we'll be giving you some great examples of some of the work that we're doing. So I want to begin by just talking about this concept that Brian mentioned around maps for machines, which is really the focus of what we do here at Voxelmaps. So starting, what's the difference between a human map versus a machine map? So human maps we're all used to. We use them in our phones and in our cars or on the web. And they're really around a kind of a use case of navigating people to an address, whether that's a city or a street or a building. That's the primary use case. The secondary use case is very much around visualization. So where we're taking some form of geodata and we're placing it on a map to visualize. The majority of the data for humans is 2D. There are some 3D aspects, but still it's pretty small. And it's pretty low resolution. So we're talking 1 to 3 meters in terms of accuracy. And for most human applications, that's totally fine. We can decide where we want to walk or where we want to drive. But when we start to look at machines, they have a different requirement in terms of the mapping and the map data. So really, machine maps are very much around creating models. So we're creating true 3D spatial models of the environment, everything that we're mapping. And so subsequently, we're analyzing everything that we can see in a given environment. So in urban areas and cities, that can be infrastructure, telecoms, utilities, but in non-urban environments, that can be things like vegetation, land structures, for example. And we're doing this at very high resolutions, so 1 to 4 centimeters. And at that kind of resolution, it's not just about the location of the objects, but also about the additional information we can pull out based on those objects. So measurements, features, attributes, which are obviously very important. So when we talk about machines, we're talking about everything from computer models and artificial intelligence models to better understand cities and environments, all the way through to future forms of autonomy. So things like autonomous cars, delivery robots, AMRs, which are automated miniature robots, drones, for example. And the requirement for this data is everywhere. So obviously the biggest use case is typically outdoor, but there's indoor use cases, there's subterranean, there's even a need for ocean data as well in the future. That's one of the things. So I want to take some time just to introduce the concept of volumetric mapping and what voxels are as well. So the starting point for this is to have a look at 3D maps as they stand today. So this is an example from Google, but you can see very similar products from Apple or here, for example, or Mapbox. And this map is a great map for humans to visualize. It's an approximate visualization of a city. It looks great, but when you actually zoom in and look at these structures, they're pretty low resolution. So really this map is built up of these very basic 3D objects with some kind of a texture and a mesh placed on it. So using a mesh is great as a visualization tool, but if we really want to get detail, if we want to see what's inside, for example, the building, there's nothing there, it's just empty. And that's because when we're looking at 3D mesh technology, meshes are only really focused on one aspect of physical matter, and that's the surface information. They're not really concerned with the interior information. And even if you were to try and map the interior and create another mesh, trying to get these two meshes to merge together is actually very complicated, very manual in a lot of ways, and subsequently requires a lot of pre-processing work to try and do this. Volumetric mapping is very different. Essentially, we use an approach which uses voxels, which I'll introduce on the next slide. But essentially what we're doing is we're able to map not only the physical surfaces of matter of cities, but also the interior information in the same model. And it's designed in such a way that this data can be automatically collected, automatically processed, and dropped straight into the model. So that has the ability then to have real-time updates of the data without having to do a lot of pre-processing as well, while still maintaining very high accuracy, 1 to 4 centimeters, and also adding a fourth dimension of time to be able to do things like change detection. So the technology that we have is based around voxels. I'm sure some of you might have heard of voxels, and voxels by themselves are not necessarily new technology. Voxel is just a volumetric pixel. Essentially, it's a cube. And voxels have been used in computer games for a long time. So for example, Minecraft is an example of a voxel rendered world. But in particular, what we do is we use voxels in a configuration called a VOG, or a voxel occupancy grid. And this technology really came out of robotics, whereby you'd have a small kind of miniature robot with a 3D scanner, very often a LiDAR on top of it. And it would go and make a very basic 3D mesh of a room so it could navigate its way around. So we took this concept of VOGs, but we applied it onto a planetary level. So the technology is actually something called an MR-VOG, or a multi-resolutional voxel occupancy grid. So what we did is we placed the Earth, or placed a giant megavoxel over the top of the planet. Now, this voxel is then comprised of multi-resolutional voxels, which theoretically can be absolutely any size, but for our purposes, we use 8-meter voxels down to 1 centimeter voxels. So this 3D mesh goes straight through the planet. It goes through everything. Wherever you're sat at the moment is full of these virtual voxels, straight through the Earth, the oceans, the buildings. And it's something called an Earth-centered, Earth-fixed model. And each voxel has a permanent position in space and it has a unique address. But to start with, it's blank. It's just a 3D or 4D georeference frame. So what we do is we validate the occupancy status of the voxel. Basically, is it free space or is there something inside it? The main way we do this is using LiDAR sensors. So if the laser from the LiDAR passes through a voxel and is not reflected off anything, we label this as free space. But the moment that the laser is reflected off a surface, we label this as occupied. So in essence, what we're doing is etching out the matter of the planet. But because we're putting it into this voxel occupancy grid, at its core, it's a global spatial database for all of this information. So it's what we call real time. It's persistent. It's always on. We don't view 3D data just as some files you put into a 3D viewer or a games engine just to process them. This is designed to handle thousands of petabytes, really planetary scale data, and being able to do the kind of analysis across the entire data set, not just small subsets of the data as well. The reason, one of the key reasons that we decided to really go with voxels over traditional technologies in 3D like points or meshes is some of the really smart features that they have. So firstly, voxels are measurement units. So it's very easy to perform calculations in 3D on any of the objects that we see, location, size, all of those things. But in addition to that, we can place additional layers of data on the surface of the voxels. So this really is an aspect of color. This can be RGB values from cameras. It could be hyperspectral imagery. It could even be things like radar. So once you've got the shape of things made out of the voxels, you've got the surface information, which gives an aspect of color, we can then get our artificial intelligence platform to start looking at the voxels in 3D and recognizing the objects and perform calculations and measurements. And this is truly done in 3D. It's not some kind of 2D image-based segmentation. We're really looking at the objects in 3D. But not only in 3D. So we can look at what is there at the moment, but then each voxel has an infinite number of time states. So we have this temporal data component. And that means that we can get the AI to also look at the data that has been there before and compare and contrast the two. So it gives us the ability to do some quite powerful change detection in the approach. And then when we combine this with the permanent addressing, the global spatial database, the ability to intelligently search and pull back information, it becomes a really powerful platform for digital twins. It's really a superior technology for building a digital twin. So I want to show you what this looks like. So to start with, this is the occupancy data alone. This is all made out of voxels. And then on the surface of the voxels, we're putting the colors from the camera. And then we're getting the AI to do the recognition. So all of these pretty colors you see here is the AI automatically recognizing a feature and vectorizing it. And once we've done that, we can then play around with the data. We can remove the things we're not interested in or export them out into different formats or put them back and analyze everything. We have full flexibility to explore the data sets that we have. We've currently trained the system to recognize about 100 different objects within cities. We'll be up to about 200 objects within the next 3 months or so. But we have the ability to train the system to recognize anything else that a customer might require, both outdoors and indoors. So around that, this is the bit where we really kind of engage with the artificial intelligence. So it's a platform we built called Voxel Insights. So we take the voxel data, and then when we apply the artificial intelligence, it gives us the insights. So this is an application that we give to customers. They can access either on their desktop or via the web. There's even a virtual reality version and an AR version as well to use. But it's from this application that you can export all the data. So you can see here all of the colorful lines and boxes. This is a recognition event. So the AI is recognizing an object, is measuring an object, and then you have the ability to export any size of data into any format that you want. But also from this platform, you have the ability then to do things like virtual surveys. So you have the ability to go into the data and explore it, even walk around the data if you have your VR headsets as well. Another aspect is really on this 4D change detection, which I mentioned before. So I just want to mention an example, and Brian's going to tell you more about this particular example as a customer use case as well. But this is just one illustration of this 4D concept working. So here we have a pole, and the pole's been mapped numerous times, but there's been a new installation on the pole, and the system is able to detect that new installation. If it's trained, it can tell you what the installation is and alert you to it. But even if it isn't trained, it can still detect the change and alert you that something has changed on there as well. So this has a lot of applications in terms of surveying, compliance around infrastructure installations as well. We also provide a lot of tools to go with the data. We can do the full training, we can do the full collection for customers, but sometimes we like to give the customers flexibility as well. So in addition to the web interface, we have the ability to provide AI training tools. So in this video, this is somebody marking up trees, it can be any object, which then is used to train the AI. And once the AI is trained, it can run through the entire data sets and pull back the features that people are looking for. So it's a really powerful and flexible application there. So that was the underlying technology, that was the insight. I'm going to talk for a few moments really on the data collection side and how we collect this data. So we have our own mobile mapping solution. It's a device called Symbo. And essentially, we've really designed this to be easy to deploy and scale en masse, in terms of going out and mapping entire cities, states, even countries as well. So the device is designed to be installed onto any vehicle that has a rack. It's about a 10-minute install for one person. At the end of the day, it takes 5 minutes to take off the vehicle, and it can be stored in a Pelican case. And that's very useful in terms of handling the logistics. In terms of if you're driving around the city or driving around the state, you have the flexibility of moving these devices around very, very easily as well. The other nice thing inside this device, we have LiDAR, we have cameras, we have high accuracy GPS and IMUs with the ability to use things like RTK, PPK. It's also powered by NVIDIA graphics cards, which means it does all of the processing on the edge. You don't need to connect this to another computer. In fact, the only thing you need to operate this is an iPad. And if there is 5G connection, you can have the ability as well to actually stream the data in real time off the device in 5G. Now, the majority of 5G installations aren't across the whole of the country yet. So if there's no 5G, you still have the ability to manually take out and swap the hard drives and process the data that way. So with some customers, we will do all of the collection ourselves and we will just deliver a product to them. With other customers, they're also interested in actually doing some of the collection work themselves. In addition to the hardware, there are a number of tools which start to make it a lot easier to do mapping and mapping missions. And so we have a back-end system which is really designed to look at an area. Again, it can be anything from a city all the way up to a country, and to divide the area up into daily mapping missions for operators. And once that's cut up, it allows then the missions to be sent directly to the users, the operators of the device, which they get to see on their iPads. They get to select the mission that they want to go and how they want to go and map. And it gives them guidance in terms of making it an optimized route for collecting data. And so once they've accepted the mission, this is the interface they see on the iPad, which just gives a very kind of nice user-friendly interface in terms of whether the system's working, if all of the green lights are on, everything's good. You have the ability then to see the data as it's being collected. If everything is green, there's no problems. But if there are problems, then the line that you leave as you're driving will change to amber or to red. And that's really important because if there are problems with the data, you have the ability to go back and collect there and then, versus working out much later, in post-processing, that there's some errors with the data as well. So there's a lot of flexibility. There's lots of tools as well to be able to troubleshoot should you ever need to. And because of the connection that these devices have, we have the ability as well to remotely support as well. So we can remotely connect to the device and do any kind of support that might be needed as well. It's a really powerful and kind of flexible product. So when we add all of these things together, what are the key benefits for using Voxel's technology? So firstly, it allows you to map much faster, creating maps and digital twins and extracting assets incredibly quickly. it's not about just mapping where these things are, it's also about pulling back insights. So even when we're recognizing objects such as a street light, it's not just the measurements, we're pulling back 14 or 15 different attributes and features. So you get an exceptionally rich data set without having to put in a lot of work. Essentially, the majority of the work and the heavy lifting is done by the Insights platform and the artificial intelligence. And so all of that combined means that you can reduce costs. One machine replaces the need of a lot of the standard survey approach that we see very often in these kind of mapping exercises. And the fact that it can all be operated by one person, not having to have two people in a vehicle or two people to set up a system, just means it's easier as well to deploy. But most importantly, creating the digital twin using Voxel Maps means that you're mapping everything that as you go through it, even if you're just interested in a few assets. So you have the ability later on to go in and to automatically extract additional features and additional assets which may be needed that maybe you didn't even know were required at the time. So it gives you this kind of full flexibility. Just before I hand back over to Brian, I want to tell everybody about a really exciting program that we've got on at the moment around, we call it the 100 cities model. It's a data as a service model. So we have different ways of operating. One way is that we will go out and do mapping missions and map an area for clients. Another way is that we are mapping ourselves and we have that data to be able to resell. So starting this year and into next year, we're mapping 100 of the top cities or metro areas around the US. And so this is a full Voxel 3D digital twin of those areas, but it also includes data such as the LiDAR point cloud, the high resolution imagery, and we break it down in terms of the road networks. And we also extract all of the features that I was showing you before into a vectorized data set. So it's very easy to export out into different formats. And we can deliver all of that data either through our web interface, so the data as a service model, or if it's a large amount of data, if people want entire cities or states, for example, then we have the ability to send that via things like Amazon S3 or even FTP or physical hard drives if required. So again, if those, we'll be very happy to share a list of those cities. But if it's of interest, then we can definitely send you data samples, and it'd be really great to look at some of the use cases. So with that, I'm going to hand back over to Brian to continue with the next part of the webinar. Thank you very much.
Thanks, Peter. So Peter gave us a really good overview of the whole concept of maps for machines and 4D volumetric mapping, and we're really excited about this 100 Cities project. What I'd like to do is to talk a little bit about some applications and use cases of the technology that we've seen and we're interacting with both customers as well as prospects. There's a number of use cases. So it doesn't have to be in one particular industry. So these are just some types of applications that we're supporting. So on the utility side, it could be joint use for transportation organizations that may be ADA compliance, right, or curb and gutter, or local governments for signage inventory, or disaster assessment, or public works and maybe interested in drainage for stormwater runoff. So there's lots of different applications that the Voxel data and Voxel technology is being used in today. A couple of projects that we've done. So in this case, it was a company that wanted a collection of traffic signs throughout a general area. This happened to be in the San Francisco area, and they're a navigation mapping company. And so what we did was we took our systems, drove the streets, and then we did a automated sign recognition collection or extraction, I should say, using the Voxelmaps AI ML technology, and then exported all that to XML for delivery to the customer. Key thing here is that over 7 million signs were actually mapped as part of this process. So quite a few signs. I think this kind of shows too that to our ability to scale for larger projects, or whether it's a small municipality or whether it's a huge statewide organization or a nationwide collect. We've been involved in those sorts of use cases up to this point in time. Another use case is installation compliance. So this had to be a local government. They wanted to look at a change detection on existing assets. So if you remember the slide that Peter talked to with the voxel structure and this whole 4D capability, in this case, it was very valuable because we had an existing data set that the customer had collected, put that into the voxel structure, and we drove the area and then took that data into the voxel structure and did a simple change detection. So being able to identify places where new signage, maybe work on an intersection where there was different curbs put in for what we talked about before, ADA compliance, but it also allowed for automatic measurements as well, automated measurements. So you can know if a sign within the right of way is a little too large for the zoning restrictions. And that really is the non-compliance. So using it to not only support identification, but non-compliance across a local government organization. Lots of example use cases across the whole automated asset mapping and the city infrastructure. So, we're data agnostic. So, up in the upper right-hand corner, some the data that we drove and merged it with some existing 3D models that have been taken via LiDAR. So there's lots of different use cases on the whole infrastructure side, whether it's looking at pavements, the right of way, could be cities looking at health of trees within their right of way and the type of trees, the volume of those trees, and potential vegetation management issues in that case. Another area where we've done a lot of work is road network mapping. So we did some work for a major automotive company. It's a lot of miles that we drove last year. We drove just over 650,000 miles in the US last year on a project. And so that's about 50 times to the moon and back. It's a lot of driving, or excuse me, 50 times around the equator, sorry. But that's a lot of driving. So we can scale up and get Voxelmaps team members out in the field to do this and collecting, not quite 24/7, but substantial amount of time. And then for this particular customer, we were looking at creating HD maps for autonomous vehicles. I'll talk a little bit about that later, but creating the road lane model, identification of traffic signs, and striping in the roadway, et cetera, and then providing that to the customer for their use in their HD map required application. Not everybody, but most people are talking about smart cities, and there's lots of capability, lots of use cases within the smart cities area where the Voxel technology can really be leveraged. So, traffic monitoring. Good thing about LiDAR is it doesn't need to be light out. So you could use that to monitor traffic, as they go through intersections or along a major motorway, day and night. You can also use it to identify vehicle type, and, smart cities can use this data to identify where they have some specific problems with traffic. It can also be used as in pedestrian monitoring. So, using it to identify high pedestrian traffic locations. This could be with LiDAR, but also can be, integrating LiDAR with the mobile phone usage as well. They can use it to identify where they need to put in more sidewalks, et cetera. And then in today's world with these pandemics, where social distancing is required, needed, they can also use this technology to help monitor pedestrians and make recommendations to use alternate routes. And then in the area of security management, so, real-time detection and tracking of people and assets or vehicles, like a public works, we want to keep track of all their assets. And then, in the, you can actually fine tune the LiDAR as well for like perimeter alarms. So if somebody moves into that area, you can actually use the LiDAR to do a really quick change detection to identify if somebody is inside the fence. So And then in the area of digital twins, so there's, lots of different applications across. I can't think of an industry that could not use digital twins. So this is an area of significant growth across, city mapping or, disaster management, cover and response, or construction monitoring, or updating base maps data, or urban environmental changes. There's the new infrastructure bill that is expected to be passed. Has about $45 billion in there, I think, for geospatial oriented requirements that governments have. And so I'll throw this out right now, but we put together a program guidebook that you'll receive a link to that has some information about the webinars, but it also has a number of pages that talk to the infrastructure bill that's coming up and what it means for geospatial. So I think everyone on this call, I would take the time to read those 4 pages, because there's lots of opportunity for everyone here in terms of leveraging some of this infrastructure funding to help us do better planning and build digital twins. Another area that was mentioned by Peter earlier on is this whole area of there's something on my screen. This whole indoor visual positioning, or VPS, and using that for automated miniature robots. And so what I've seen is that, not only are we worried about collecting the digital twins of the external of the building, but also the internal working. So I do have a quick demo here I'd like to show. Just move it up a little bit. And so you can see, this is the bottom picture, is the voxelized image using the RGB values and in real time colorizing the model. The upper left is the actual imagery being taken by the robot, and the upper right is, you can see it scanning in real time, coming in, scanning the entire office, backing out. There's lots of different capabilities for people to use this, especially in indoor environments. It can be a miniature robot like this. I've seen people use backpacks as well. So there are lots of different capabilities to use this for a number of applications. On the utility side, like things like asset inventory. So using, in this case, the asset capture was done via aerial lidar. So as Peter mentioned, we're data agnostic, or I should say source agnostic, because it really doesn't matter where the content comes from. We can use that, consume that within the Voxel 4D volumetric mapping structure, and then provide a quality output product to the customer. We did, in this case, we consumed the aerial LiDAR data, and then used our AI ML automated feature extraction to actually pull out different types of poles, lines, substations, etc., and then validate that against the actual spatial database that particular customer had. Another area too of significant interest is the whole vegetation management. This has been pushed forward by a lot of utility organizations based on issues that several of the investor-owned utilities in California had with vegetation touching wire. So you can see here we have the upper right-hand corner. This is a picture of the street that we drove down using the symbol system collected. This is the imagery itself, and then we took the LiDAR and put the RGB value of every voxel in there, and then we can use that to do extraction. So here we've extracted the poles, we've extracted wires, we've extracted the veg, and then you can identify and create buffers around the conductor lines to find out where there's vegetation encroachment within that. And then what's nice is that I can then buffer and overlay, use that to determine any encroachment issues, but then I have the back end data to quantify that vegetation. I can take that data, hand it off to my teams that would then deploy a truck out there to do some vegetation removal. But before they even hit the hit the street, they know how much vegetation and where, and along what conductor wires need to be worked on. There's also this whole area of in vegetation management, as I mentioned, and this is an interesting one here in the lower right. You can see here where we've actually pulled out the vegetation that's was too close to the wire, just to give a view. So each one of these could be just basically a layer of data that you could use to do quantification of where the issues are. So again, the same sort of thing. We drove the area, did the extraction. The lower left here, you can see where we found everything red in the vegetation layer is where we saw vegetation encroachment. So it's a significant industry across most municipalities and utility companies. I'd mentioned before change detection. So in this case, it was a change detection on telecommunications equipment. So in this case, the customer, we had a database of data that we had collected in their service area. And then they had a number of 5G antennas that got placed on poles. And so all they were looking for is identify the new assets, being the antennas, and on which particular pole, right? And so we went out and did the secondary collect, did the automated extraction. In this case, you see here in the middle, pulling out that particular object, and then using that to validate what had been done and validate it against the contractor's work orders. So it's a great tool to use for them to identify areas of compliance, non-compliance, and location of new assets. In this case, it could have been that they put it on the wrong pole and they actually wanted that antenna on the pole to the right facing the other direction. So it's a great compliance tool for that particular customer. And then we've seen lots of interest in the telecommunications organizations to talk about using digital twins to identify and validate signal strength. So in this case, building a digital twin of geography. And so we did both external and internal. Their office building, we went in and did some data collection inside, but we also drove the outside as well. So we create this true digital twin. And then we ran the signal attenuation and propagation models from those 5 known 5G asset antenna locations and used it to try to determine gaps. And again, this was both internal and external. So inside of the building, based on nearness to windows or whether it's an interior office, et cetera, they were able to identify where they had coverage issues. So it's a really good model for them to use to provide their customers with a higher service. And then the automated HD map creation. So in this case, collecting very high resolution data that can be used for the autonomous vehicles. So signage, heights of bridges, things like that. So that in the HD map itself, you'd have the dimensions, et cetera, of your car within the system, and it'll tell you whether or not you can drive that delivery truck through that tunnel or down the street because of low hanging wires. So there's lots of different capabilities on the autonomous vehicle side. And autonomous vehicles in the smart city concept is something you're going to see more and more and more across most municipalities. So we can have autonomous vehicles capturing LiDAR could actually replace some area collections. It'll never replace it all at all. I think it's a good complement to what the aerial LiDAR collection. It's just that it can provide much more detailed content. And then this whole concept that we're promoting called the constant collection networks, or I call it C2N. So collecting and in real time transmitting that information to a central database to provide road conditions and roadway systems to other vehicles. And then smart city connections in the city itself with this whole vehicle to everything. So using just the vehicle itself as just another IoT sensor, and it can be used for emergency management, or relaying road hazards in the road. Somebody, a rock fall or something like that. Very supportive of transportation planning, and then this area of smart parking, where the whole vehicle to everything and LiDAR could identify open spots and relay that information to existing automated vehicles and navigate to open spots and save on fuel consumption. It was interesting in doing some research in the whole automated parking. There's about 4 or 5 parking slots per vehicle in the United States. But it just seems like every time I go someplace, I can't find a place to spot to park in those. I also want to talk a little bit about HD map creation. So in today's model, organizations go out and do the road data collection. So they do the collection and harvesting via these HD mobile mapping sensors. And then many times those hard disk drives are physically shipped to a data center because there's too much data to collect every day and upload. So that's in the data centers where all the raw processing, data corrections, maybe PPK corrections, and then putting that into a Voxel data, the Voxel data model. We can then do the AI feature extraction and the feature vectorization, and really create this high definition HD map, and then updating that map display within the vehicles on the road. So that can take a significant amount of time. So what we've seen is 1 to 2 weeks for this process, and about a month for actually getting the data to the end customer, which, if you think about that, 6 weeks, that's actually a pretty short time period if you think about in the grand scheme of things. However, we had a customer who said, how can we change that model? What can we do? So we engaged on a proof of concept with Verizon and Amazon Web Services. So in this case, same collection system, the Symbo that Peter talked about earlier, but we put a Wi-Fi antenna on the Symbo. So we were able to do the collection. The data was sent via Verizon's 5G Edge. At the facility, at the Verizon facility, are the AWS wavelength instance. So instead of having to hit the telecommunications and then across the internet to AWS, it's actually the wavelength is actually on location at the telco. We then took that data, we were focused on the LiDAR side of things, and created an updated map and delivered it back to the vehicle in 15 seconds. So collection through the 5G edge and wavelength, create the 3D model, back in the car, displayed in the vehicle, a full 3D model, and that became 15 seconds. So pretty significant turnaround from the 6 weeks to 15 seconds. So it's a very exciting area. Peter was actually part of a presentation 3 or 4 weeks ago at Mobile World Congress in Barcelona with Verizon and AWS on this particular project. So let me just show you. This is the data. It's coming in blocks. Obviously, this isn't the speed at which our drivers were driving down the street, but it just shows you all the information that we were able to collect and then automatically extract to get the roadways, all the poles, all the utility lines, all the vegetation, et cetera, in a very quick and fast period of time. Like I said, within 15 seconds, it would return the data to the end customer. So we've covered a lot today. Peter gave us a very solid overview of the Voxelmaps as a company, talked about this whole concept of maps for machines, and I just asked, think about that. Think about that as you move forward. With everything going towards machine learning, is the data I'm collecting really the right data that my machine needs? He then talked about the volumetric mapping and our technology, the data collection network, and then briefly discussed the 100 cities DAS data set. I have then given some overview of some of the potential industry use cases. There's many, many more. We're love to talk to you about doing that. So what I'd like to do is I would like to open it up for questions. And we do have a number of questions. One was on pricing. So how do you price your product? So it's a pretty broad pricing model that we can use. So Peter mentioned the whole data as a service, or FTP, where we deliver that data to you. That data can be licensed, meaning licensed to use, or you could have full ownership based on your project. It kind of really depends upon how you want to work. And then we can price it by linear mile, which we do most often. But for some organizations, they say, we just want the light poles, right? We just want that. That's the only thing we want. So we can do a per asset model as well. It's really kind of up to you. So if there's an interest, let's connect and talk a little bit about pricing. A couple ones here. What about dynamic objects like people and autonomous vehicles? What is their address? So, Peter, can you address that?
Yeah, no, it's a really, really great question. So one of the great things that we do, so as soon as the data is collected and converted into voxels, the Voxel Insight platform not only extracts the features we're interested in, but it uses deep learning to remove the features we're not interested in. So by default, we remove people, we remove cyclists, cars, dogs, animals, etc., all from the scene automatically. And we don't do this using kind of very basic techniques like KF filters, which can cause a lot of problems, a lot of errors. We're using deep learning to be able to do that. So in effect, they don't have an address. They're removed from the scene.
Cool, thank you. So since this one talked about people, Alex actually asked, it seems public identification and monitoring poses a serious privacy and security. Maybe it's more of a statement than a question.
Yeah, maybe I can a couple of
points. Yeah, that could be back to that use case I was talking about, where you do monitoring of people on the street and stuff.
Yeah, so generally speaking, particularly this is important depending on where you're collecting the data in the world, but there's definitely information bodies where you have to protect privacy. So even when you're collecting, doing a mapping collect, and you remove the people or personally identifiable information such as number plates from the scene. So you have the ability that the platform actually obviously removes that, as I just mentioned, but it can remove that as well from imagery. Where you're monitoring people is a different use case. And so the client there has to be law enforcement, or it has to be a government body with permission to do that. Otherwise, obviously, that's not allowed.
Right. Another good question, why does AI work better with voxels?
Yeah, really good question. So it's not that it works better with voxels, it works better in 3D. So if you're looking at trying to detect an object and just using a flat 2D image, and just using the pixels, that's one thing. But if you really get the ability to look in 3D at objects, you get a much, much higher recognition. And so the approach, you've got two ways to recognize in 3D. We either train to recognize points and point clouds, but point cloud data can be very unruly. It's particularly if you're doing multiple passes of data, trying to get all the points to align becomes a very messy data set over time. Or use something like voxels, which become very powerful. So the fact is better than 2D recognition is because of the 3D versus just using a 2D flat image.
Great, thank you. Is our data natively consumable using Esri technology?
Yes, and we're an Esri partner as well. So we're building connections as well. So we can export out into the format, so you can use it directly in Esri. But very soon we'll be connecting it via APIs as well, so it'll be seamless between the platforms.
Okay. Another question, do you have pre-trained models ready? And how do you QC the outputs after the feature's been extracted?
Yeah, again, another really good question. So yes, absolutely. So I mentioned that the systems are already trained to recognize about 100 different assets in cities. There's even more assets actually that we do internally. So we have pre-trained models. Now, the training process is quite extensive on our side. So we have teams that go through and annotate the data in 3D, train the AI and the engine on training data sets, test data sets, where we get to validate the QA. So we have a very dedicated QA phase there as well. Then depending on the outputs, we may introduce another level of QA, which might be required for our customer, for example. If you're training yourselves, which is totally an option, we provide tools to do that, and we would guide you through that process. But definitely, it's good to have QA as part of that.
Okay. And then the follow-on to that was any specific tools that we have, and do we process on the desktop or the cloud?
So everything's processed. We have a private cloud and we have public clouds as well. And so the data processing that we do is actually done on the private cloud. But then once we've processed there, we store in public clouds, and that's accessible then to customers. The way that you can access it, you've got different routes. You can either use a web interface or you can use a desktop application. The desktop application is very good if you're doing training or doing a lot of exploring of the data in detail, or even virtual reality, for example. All of them still connect to the same data set.
All right. So if someone said they're very interested, how to best to contact you. So the two contacts, Peter or myself, feel free to reach out to us at the emails there. We'll also, as part of the program guidebook that we'll be sending you a link to, that will have our contact information. So you can do that. Here's a question. Can the voxel data be converted to traditional points and 3D polylines for consumption in traditional CAD environments like Autodesk Civil 3D or Vegetation Management?
Yeah, absolutely. So really, when you think about the Voxel platform, while we collect, store, process in voxels, and you have the full ability to do pretty much every calculation you can imagine within the 3D environment, within the Voxel environment, you also have the ability to export out into pretty much any data set. So even if you wanted to export out points, we can take the centroid, for example, of all of the points of the voxels and convert into a point cloud. But we also support a number of CAD formats as well. So you can export out into a format that allows you to manipulate the data maybe in different ways or different workflows that you might have already.
Okay. So a comment and a question. So it seems like most of the applications we talked about were focused on urban applications. So is there any other applications outside of urban that we can address? And also, do we primarily work with LiDAR-based remote sensing data, or do we ingest and work with other types of remote sensing data and imagery?
Yeah, again, great question. So obviously in this talk, we haven't really touched on the non-urban environments, but we do quite a lot. So we teamed up with a project called the Earth Archive, where they're looking to do aerial LiDAR mapping of jungles, of forests around the world. And we use our technology for those applications. And so we can do things like foliage penetration. So we can see underneath the tree canopies, remove the trees. We can detect abnormal structures or human-made structures. We can even count individual trees within a forest, for example, for carbon accounting or forestry health. So there's lots of other applications there. Maybe it'd be a good idea, we can do a webinar on those kind of applications at some point. But also, if you have a look at our YouTube channel, the presentations we gave actually with the Earth Archive, also with NASA, those are available there, and you'll be able to see some of those examples.
Yeah, I was going to suggest going to the YouTube channel to see some of the videos that we put together for non-urban applications, and then if people are interested, the Earth Archive's website as well is a good source of information on some of the things that we can do. What about underwater volumetrics for dredging?
Yeah, so in my presentation, actually on the third slide where I compare human maps and machine maps, there's a line at the bottom which we talk about what type of data, where are we collecting data, outdoors, indoors, subterranean, and ocean. So we are starting to collect ocean data. It's very early days. Obviously, we're doing that aerial. It's not done via other platforms. But in principle, yes. And we have a couple of partner companies which are giving us data sets, which we then voxelize and apply different voxel technology essentially to as well. So it's early days with ocean data. Absolutely, we can do it, but something that we're also interested in exploring.
Right. How does the application perform on, it says on rotary collected data? Is there a minimum point density requirement, and can this be hosted 100% on shore?
Not sure I quite understand that. Perform on collected data?
Yeah, rotary collected data. I'm not sure. Jacob, I may just reach out to you, or you could identify what you're really looking for here. Do you post-process the location data to improve its geospatial accuracy and to possibly refine historic collections?
Yeah, so with our data sets, absolutely, to get down to, resolution is one thing, but, the accuracy as well, absolute positional accuracy on the planet is very important. And that uses a number of techniques. So we do use corrections like RTK, PPK, and there's also other technologies essentially that we use to position the data to really get it to that degree of accuracy. So it's a whole kind of location stack to achieve that in the post-processing.
Right. And then the solution that I talked about, the 5G based real-time mapping, near real-time mapping, we talked about doing that with Verizon. The question is, will it work with other service providers, especially in other countries?
Absolutely. So in fact, Verizon was the first partner and customer that we worked with to deploy this solution and kind of show that we can do this real-time concept of mapping and real-time update, which is really important. But the technology will work with any 5G connection. The issue is 5G isn't everywhere. And even when 5G is deployed at the moment, it's kind of very throttled, so it depends really where the 5G, the kind of technology that's being deployed as well. But if it's full 5G and we've got the bandwidth, then absolutely that will work, and it can work with any network as well.
Right. And the rotary collection model that Jacob was talking about was via helicopter for corridors.
Oh yeah, sure.
Yeah, which we worked with a number of people.
Absolutely. In fact, we just finished doing an aerial scan of San Francisco using helicopter and aerial LiDAR and imagery, and that data drops into the model alongside the data that we've collected ourselves with our mobile sensors as well. So absolutely, we can do that.
Okay. Well, there are a couple more questions, but we're really out of time. We want to shut this down before top of the hour. So what I'd like to do again, just we appreciate everybody's participation. On those of you that had submitted additional questions, I'll just reach out to you directly if possible. And if you have any specific questions or want to engage in a conversation with us, feel free to reach out to either Peter or I at the email addresses presented there, or feel free to call me on my phone as well. So again, we appreciate your participating with us today. We do have 3 other webinars in the series. So on Thursday, we have one that's focused a bit more on transportation. Next Tuesday, the 24th, on utilities. And then Thursday, on the 26th, is another overview. So it's basically the same webinar. So we'd love to have you participate in the utilities or transportation, but you'll find that the content of next Thursdays is going to be the same as this. So just an FYI. And again, we'll send you a guidebook that talks about the webinars. And as I mentioned, we've got some good information in there about the infrastructure bill and the opportunities for you in the geospatial community. Appreciate your time. Thank you.
Thanks, everyone. Bye-bye.